Picture this. You're standing in a Ford engineering lab in Dearborn, Michigan. It's 3 in the morning, sometime in the fall of 1963. The fluorescent lights are buzzing overhead, coffee cups are scattered across every flat surface, and a group of exhausted engineers are gathered around a dynamometer that's about to change American motorsport forever. The needle on the gauge climbs past 580, past 590, past 600 horsepower, and the room erupts, not in cheers, but in stunned silence. Because every single person in that room knows they've just built something that no racing sanctioning body on the planet is prepared to deal with. They've built an engine so advanced, so powerful, so far ahead of everything else in American racing that it will be banned before it ever turns a competitive lap. And that ban, that single decision made in a back office in Daytona Beach by a man who built stock car racing with his bare hands, will ripple through 6 decades of motorsport and shape every single engine rule you see on a NASCAR grid today. This is legacy motoring, and I spend way too much time thinking about engines that were too good for their own era. If you're someone who obsesses over the intersection of engineering brilliance and racing politics, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now look, most people know the basics of this story. Ford built an overhead cam 427, NASCAR said no, Ford got mad, the end. But here's what most people don't realize. The real story of the Ford 427 SOHC, the engine everyone calls the Cammer, isn't just about one engine getting banned from one racing series. It's about corporate warfare between the 3 biggest automakers in the world. It's about a father and son who controlled American racing like medieval kings. It's about an engineer who looked at European Formula One technology and asked the most dangerous question in motorsport. What if we put that in a stock car? And it's about how a rulebook decision that seemed small at the time created a philosophical divide in racing that still exists today. Push rods versus overhead cams, tradition versus innovation, America versus the world. To really understand this story, we need to go back before the Cammer even existed. We need to go back to February 1963, to the high banks of Daytona International Speedway, where Ford Motor Company experienced what insiders later described as the most embarrassing day in the company's racing history. The 1963 Daytona 500 was supposed to be Ford's moment. They had poured millions into their racing program. They had the best drivers, the best teams, the best preparation. What they didn't have was an answer for Chrysler's new 426 Max Wedge engines, which were tearing apart the competition. Now, Junior Johnson actually won that race in a Chevrolet, which is its own interesting story, but the real narrative was how badly the Fords were outclassed by the Mopars throughout the entire speed weeks. Ford's top wedge engines were making somewhere around 410 to 420 horsepower on a good day, and Chrysler's engineers were pulling numbers that made Ford's power output look like a production sedan. But here's the thing, that 1963 embarrassment was just the appetizer. The real gut punch came 1 year later, in February 1964, when Chrysler unleashed the 426 Hemi on an unsuspecting field at Daytona. And I don't mean they won, I mean they annihilated everyone. Richard Petty took the checkered flag in the Daytona 500 that year, and Plymouth swept the top 3 positions. The Hemis were so dominant that Ford's cars looked like they were racing in a completely different series. Some estimates suggest the Hemi was making 425 to 435 horsepower in race trim, with a single 4-barrel, and with the dual quad setup that NASCAR allowed at the time, those numbers climbed even higher. Now here's where the story gets really interesting. Because what most people don't know is that Ford's response to the Hemi didn't start after the 1964 Daytona debacle. It started after the 1963 season. Henry Ford II, the man who ran the company his grandfather built, was not the kind of executive who accepted losing gracefully. According to multiple accounts from people who were in the room, Henry Ford II issued what became known internally as the directive, and the directive was simple. Build something that makes the Hemi look like a lawnmower engine. Cost is not a factor. Timeline is yesterday. The assignment landed on the desk of a man named Bill Innes, though some sources spell it Ennis, who ran Ford's Special Vehicles Engineering Group. Innes was not your typical Detroit engine guy. He had spent time working on Ford's Indianapolis 500 program, which meant he had exposure to racing engine philosophy that most American engineers never encountered. He understood that the traditional American approach to making more power, bigger displacement, bigger valves, more carburetor, had fundamental limits. The Hemi had essentially maxed out what you could do with a pushrod valve train in a hemispherical combustion chamber. Bigger pushrods, stiffer springs, more aggressive cam profiles, sure, you could squeeze out another 20 or 30 horsepower, but you were fighting diminishing returns. Innes looked at the problem differently. Instead of asking, how do we make a better pushrod engine, he asked, what if we eliminate the pushrods entirely? And that question, that single conceptual leap, led him to overhead cam technology that was already dominating Formula One and European sports car racing. Coventry Climax, Ferrari, BRM, they were all running overhead cam engines that revved higher, breathed better, and made more specific power than anything coming out of Detroit. The conventional wisdom in American racing said overhead cams were too complex, too fragile, too European for the rough-and-tumble world of stock car racing. Innes saw it differently. He saw an opportunity to leapfrog not just Chrysler, but the entire American racing establishment. Development began in earnest in March 1963, and Ford's experimental engine division in Dearborn became something resembling a wartime production facility. 3 shifts of engineers, machinists, and technicians worked around the clock. The base architecture would be Ford's existing FE block, the same fundamental structure used in their 427 wedge engines. This was a strategic decision. The FE block was already NASCAR legal, already proven strong enough for racing duty, and already in production. Everything above the deck surface, though, would be completely new. The first major engineering decision was choosing single overhead cam per bank rather than dual overhead cams. This is where Innes showed his practical genius. A DOHC setup would have been more elegant, more efficient, and would have unlocked even more potential. But it also would have been significantly more complex, harder to package in existing chassis, and would have required an entirely new cylinder head architecture. SOHC gave them 80% of the benefit at 50% of the complexity. Each camshaft would operate all 8 valves in its bank through short rocker arms, eliminating the long push rods and their associated flex, weight, and harmonic problems. But here's where it gets really interesting. The cam drive system. In a traditional overhead cam engine, you'd use a timing belt or a short chain running directly from the crankshaft to the camshaft. The FE engine's architecture made that impossible. The camshafts sat too far from the crankshaft for a direct drive. Innes' solution was audacious. A massive timing chain, roughly 6 feet long when laid out flat, running over a series of sprockets and tensioners. Each chain consisted of 174 precision-manufactured links. The chain was 1.5 inches wide and ran over 7 sprockets total, 1 on the crank, 2 idler sprockets, 2 adjustable tensioner sprockets, and 1 cam sprocket per head. The entire assembly was continuously bathed in pressurized oil fed through dedicated passages in the block and heads. Now, you might be thinking that sounds like a reliability nightmare, and initially you'd be right. The first prototype cammer fired up on the dyno sometime around June 1963. And it lasted approximately 4 minutes before it self-destructed. The valve springs couldn't handle the acceleration forces imposed by the aggressive cam profiles. The springs were collapsing, causing valve float, which led to valve-to-piston contact, total engine destruction. Prototype 2 incorporated beehive valve springs borrowed from Can-Am racing technology. These springs had variable rate coils that resisted harmonics better than traditional cylindrical springs. This engine lasted significantly longer, about 37 minutes on the dyno, before the timing chain tensioner failed. When the tensioner let go, the chain developed enough slack to jump timing on one bank. Once the cam timing shifted, the valves and pistons occupied the same space at the same time. Again, total destruction. But the engineers learned from each failure. They refined the tensioner design, improved the spring rates, adjusted the oil flow to the chain system, and by late summer 1963, Prototype 3 was on the dyno. and Prototype 3 was the one. On August 14, 1963, at approximately 2:47 in the morning, the Camry first exceeded 600 horsepower on Ford's most accurate dynamometer. Not the optimistic marketing dyno that added 10% for press releases. The real dyno, the one the engineers actually trusted. Let me walk you through what made this engine so mechanically remarkable, because the details are where the genius really lives. The cylinder heads were cast aluminum, which was itself a significant departure for Ford NASCAR engines of this era. Most American racing heads were cast iron, heavy but durable. Aluminum saved roughly 40 pounds per head, which translated to 80 pounds off the top of the engine. That weight savings mattered enormously in a stock car, where the high center of gravity of a heavy iron engine affected handling through every corner. Each aluminum head contained a single camshaft operating 8 valves, 4 intake and 4 exhaust, through rocker arms with a ratio of 1.73 to 1. That ratio was carefully chosen. A higher ratio would have multiplied the cam lift more aggressively, but would have increased stress on the valve train components. A lower ratio would have been more conservative, but would have required more aggressive cam low profiles to achieve the same valve lift. The 1.73 ratio was the sweet spot, giving them the valve motion they needed while keeping component stress within manageable limits. The valves themselves were massive. Intake valves measured 2.195 inches in diameter. Exhaust valves were 1.73 inches. Now, for comparison, Chrysler's 426 Hemi ran 2.25-inch intake valves, which were larger, but their exhaust valves were 1.94 inches. Here's where the engineering subtlety comes in. The Camry's valve angles were set at 14 degrees from the cylinder bore centerline, compared to the Hemi's 18-degree valve angle. That 4-degree difference might sound trivial, but it had enormous implications for airflow at high RPM. The shallower valve angle in the Camry created a combustion chamber shape that promoted better mixture motion and more efficient filling of the cylinder at high engine speeds. It's one of those details that separates good engine design from great engine design. The combustion chambers were hemispherical in shape, similar in concept to Chrysler's design, but the execution was distinctly Ford. The compression ratio was set at 12.5 to 1, with the race-spec pistons, which were forged aluminum pieces machined to tolerances of plus or minus 1/1000th of an inch. Let me put that in perspective. A human hair is roughly 3/1000th of an inch thick. These pistons were machined to 1/3 the width of a human hair. The connecting rods were steel forgings, chosen over aluminum for their fatigue resistance. In a racing engine that would see sustained high RPM for 500 miles, steel rods were the safer choice, despite their weight penalty. But the real magic, the part that made the Camry fundamentally different from everything else in American racing, was in the breathing. The intake and exhaust ports were designed using smoke flow visualization, which was genuinely cutting-edge technology in 1963. Engineers would create transparent replicas of the port passages and flow smoke through them while photographing the patterns with high-speed cameras. This allowed them to identify areas of turbulence, separation, and restriction that traditional flow bench testing couldn't reveal. Every surface of every port was refined through dozens of iterations, each one flowing slightly better than the last. The result was intake ports that flowed 371 cubic feet per minute at 28 inches of water pressure differential. For context, the Hemi's ports flowed approximately 320 to 330 CFM under the same conditions. That 15% advantage in airflow translated almost directly into a 15% advantage in power potential. More air in means more fuel burned means more power out. It's the fundamental equation of internal combustion, and the Camry solved it better than anything America had ever produced. The cam profiles themselves deserve special mention. In a pushrod engine, the cam lobe shape is constrained by the dynamics of the entire valve train. The lobe has to account for pushrod flex, rocker arm deflection, lifter dynamics, and the inertia of all those moving parts. This means pushrod engines can't run extremely aggressive cam profiles without risking valve float, where the valve train components can't keep up with the cam lobe and the valves start bouncing off their seats. In the cammer, with the cam sitting directly above the valves and operating them through short, stiff rocker arms, those constraints largely disappeared. The cam lobes could be far more aggressive, opening the valves faster, holding them open longer at peak lift, and closing them more quickly. The result was dramatically better cylinder filling at high RPM compared to any pushrod engine of the era. And then there was the oiling system. The camera required a completely revised lubrication system compared to the standard FE engine. Those long timing chains needed constant oil flow to prevent wear and maintain proper tension. The overhead cam bearings needed pressurized oil delivered through passages machined into the cylinder heads. Ford designed a high-volume, high-pressure oil pump that moved roughly twice the oil volume of the standard FE pump. Additional oil passages were machined into the block and heads specifically for the cam drive system. The oil pan was deepened and baffled to prevent oil starvation during high-G cornering, acceleration, and braking. The first race-ready cammer, as in a complete engine ready to be installed in a car and taken to a track, was finished on October 3, 1963. When they strapped it to the dyno with a single 4-barrel carburetor, which was what NASCAR required for competition, it produced 616 horsepower at 7,000 RPM. With dual 4-barrel carburetors, which NASCAR was considering allowing for the 1964 season, it made 657 horsepower. Peak torque was 515 pound-feet at 3,800 RPM. Those numbers were staggering. Remember, this was 1963. There were no computers designing these parts, no CAD software modeling airflow, no computational fluid dynamics simulating combustion. Everything was done with slide rules, hand calculations, physical testing, and the accumulated experience of engineers who had spent their entire careers understanding how air and fuel behave inside metal passages. The fact that they achieved 616 horsepower from a normally aspirated engine with a single carburetor in 1963 is one of the most remarkable achievements in the history of internal combustion engine development. Ford immediately submitted the engine to NASCAR for approval. The homologation rules at the time required manufacturers to produce a minimum number of engines and make them available for public purchase through their dealer network. The exact minimum number varied depending on the interpretation of the rules, but Ford committed to building 500 units. The base price would be $2,470 per engine, which translates to roughly $24,000 in today's money. That actually sounds like a bargain for 616 horsepower. But remember, in 1964, you could buy an entire Ford Galaxy for less than $3,000. NASCAR's initial response was telling. They didn't say yes, and they didn't say no. They stalled. Bill France Sr., the founder and absolute ruler of NASCAR, formed what he called a technical review committee to evaluate the engine. This committee consisted of France himself, his son, Bill France Jr., and NASCAR's technical director, Dick Beattie. 3 men, all of whom answered to Bill France Sr., would decide the fate of the most advanced racing engine America had ever produced. The committee's deliberations were not public. There were no minutes published, there were no public hearings where Ford could present their case. The decision would be made behind closed doors by a man who viewed NASCAR not as a sport governed by objective rules, but as his personal creation to be managed as he saw fit. While NASCAR deliberated, Ford kept developing. By December 1963, they had built 27 complete camera engines. They shipped one to Holman Moody, their primary NASCAR team, who installed it in a Ford Galaxy for testing at Daytona. The driver was Mario Andretti, then a rising star in American racing. Andretti's lap times at Daytona with the camera-powered Galaxy were reportedly 4.3 seconds faster than the existing track record. Not 0.4 of a second, 4.3 seconds. On a track where the difference between pole position and missing the race was often measured in hundredths of a second, the camera was in a completely different universe. Those test results almost certainly made their way to NASCAR officials, and they almost certainly terrified Bill France. Because if the camera was 4.3 seconds faster in testing, with a car that hadn't been fully optimized for the engine, the performance gap in actual competition could be even larger. Every other manufacturer would be racing for second place.
On January 15, 1964, NASCAR made its ruling. The 427 SOHC was banned from competition effective immediately. The official statement cited that the overhead cam design was not representative of American production car technology, and therefore did not meet NASCAR's requirement that engines be based on production designs available to the general public. The reasoning was, to put it politely, intellectually dishonest. Ford was literally producing the engines. They met the homologation requirements. They were being sold through Ford's dealer network. You could walk into a Ford dealership and order one. But NASCAR's rules had always contained enough ambiguity for Bill France to interpret however he saw fit. And he saw fit to keep the camera out.
Now, you might be thinking this was purely about technology, that France was some kind of traditionalist who just didn't like fancy European engine designs in his good old boy racing series. And there's some truth to that, but the real story's more complicated and more political. Here's what most people don't realize about the camera ban. It wasn't just NASCAR acting on its own judgment. Internal documents and later interviews revealed that Chrysler had threatened to withdraw from NASCAR entirely if the camera was approved. Think about that for a second. Chrysler had just spent a fortune developing the 426 Hemi, had just dominated the 1964 Daytona 500, and was finally enjoying the competitive advantage they'd been chasing for years. The camera would have made all of that irrelevant overnight. General Motors was also applying pressure behind the scenes. Officially, GM had withdrawn from racing after the 1963 AMA manufacturer's ban. Unofficially, they were still supporting teams with parts, engineering assistance, and quiet financial backing. GM had no overhead cam answer to the camera and no interest in developing one. If the camera was approved, GM's under-the-table racing involvement would become even more expensive and even harder to justify. So Bill France was facing pressure from two of the three major manufacturers to ban the engine, while only Ford wanted it approved. The math was simple. Lose one manufacturer or lose two. France chose to keep Chrysler and GM happy. Ford's reaction was volcanic. Henry Ford II personally telephoned Bill France, and according to France's secretary who was listening on the line, the conversation was extraordinarily profane. Ford's argument was straightforward and difficult to counter. Ford Motor Company sold more cars than Chrysler. Ford's involvement in NASCAR drove more ticket sales and television viewers than any other manufacturer. NASCAR needed Ford more than Ford needed NASCAR, and Ford had followed every single rule regarding engine homologation. The ban was arbitrary, politically motivated, and fundamentally unfair. France didn't budge. But he was shrewd enough to offer a compromise. The camera could run in any racing discipline except NASCAR oval racing. Drag racing? Fine. Boat racing? Fine. Bonneville speed records? Absolutely. Just not stock cars on oval tracks. And to show that he wasn't simply doing Chrysler's bidding, France also imposed restrictions on the Hemi, requiring it to run with a single 4-barrel carburetor instead of the dual quad setup that had been legal in 1964. Ford's response to the ban was a masterclass in corporate pettiness elevated to an art form. If NASCAR wouldn't let the camera race on ovals, Ford would make sure the entire world knew what they were missing. They built an additional 100 camera engines specifically for drag racing and distributed them to the most prominent drag racers in the country. The camera quickly became the dominant engine in professional drag racing, and every record it set was a middle finger directed squarely at Daytona Beach. Gas Ronda, one of the premier fuel dragster pilots of the era, put a camera in his front-engine dragster and ran 8.23 seconds at 185 miles per hour in the quarter mile. Connie Kalitta, another drag racing legend, campaigned the camera-powered car that pushed those numbers even further. By the end of 1964, camera-powered cars held virtually every significant quarter-mile record in their respective classes. Ford made sure every single one of those record runs received maximum publicity. Every press release, every magazine advertisement, every dealer promotion mentioned the camera's NASCAR ban. The subtext was always the same. This engine is too good for NASCAR. NASCAR is afraid of progress. NASCAR chose politics over performance. In February 1965, Ford tried a different approach. They submitted a de-stroked version of the camera, reduced from 427 cubic inches to 396 cubic inches, hoping that reduced displacement would make it acceptable to NASCAR. The smaller engine would theoretically produce less power and compete in a different displacement class. NASCAR rejected the application before Ford even finished the paperwork. The message was unambiguous: no overhead cams. Period. Not 427 cubic inches, not 396 cubic inches, not any cubic inches. The architecture itself was banned, regardless of displacement. Ford responded by pulling out of NASCAR entirely for the first half of the 1965 season. They redirected their racing budget to two programs: the GT40 endurance racing program aimed at beating Ferrari at Le Mans, and an expanded drag racing effort centered around the Camry. This withdrawal cost NASCAR dearly. Without Ford's factory teams, the 1965 Daytona 500 field was noticeably weakened. Television ratings dropped. Attendance at several races declined. The phone lines between Daytona Beach and Dearborn were busy all spring. By mid-1965, a fragile peace was negotiated. Ford returned to NASCAR with their pushrod 427 wedge engines, which were significantly less powerful than the Camry, but still competitive enough to race. The Camry remained banned, but Ford extracted concessions on other technical rules that helped level the playing field against the Hemi. It was a compromise that satisfied nobody completely, which is usually the sign of a successful negotiation. But while the NASCAR drama consumed the headlines, the Camry was living its best life in other forms of motorsport. In drag racing, the engine had become so dominant that the National Hot Rod Association started considering its own restrictions. By 1966, 11 of the top 16 top-fuel dragsters in the country ran Camry engines. The engine's combination of massive airflow potential, high RPM capability, and robust bottom end made it the perfect platform for the nitromethane fuel that top fuel dragsters burned. On nitro, a properly prepared Camry could exceed 1,000 horsepower from a single engine. On gasoline, with moderate modifications, 700 horsepower was achievable and reliable. Here's where the story takes a turn that almost nobody talks about. While NASCAR was using the Camry to dominate drag strips and embarrass NASCAR, the United States military came calling. The Navy was developing a new class of high-speed patrol boats for operations in Vietnam, specifically for riverine warfare in the Mekong Delta. They needed engines that were lightweight, extremely powerful, and capable of sustained high-output operation in brutal tropical conditions. The Camry, modified for marine duty with detuned cam profiles and strengthened bottom-end components, fit the requirements perfectly. Between 1965 and 1967, Ford sold approximately 234 Camry engines to the military. These engines were painted olive drab instead of Ford's signature blue, and they were installed in patrol boats that operated in some of the most dangerous waterways in Vietnam. The marine Camrys were tuned for reliability over peak power, producing around 500 horsepower in a configuration that could run for 2,000 hours between rebuilds. For a racing-derived engine, that kind of durability was remarkable. Those engines powered boats carrying American sailors through hostile territory, a far cry from the oval tracks of Daytona, but a testament to the fundamental soundness of the Camry's design. The most spectacular Camry installation, though, might have been Mickey Thompson's Challenger I land speed car. Thompson, one of the most inventive and daring racers in American history, installed 4 Camry engines in a streamlined body designed for maximum speed runs at the Bonneville Salt Flats. Each engine produced approximately 710 horsepower on nitromethane fuel, giving the car a combined output of roughly 2,840 horsepower. In 1968, the Challenger I reached 406.6 miles per hour on the Salt. Thompson believed the car was capable of 500 miles per hour, but he couldn't find tires that would survive the rotational forces at that speed. Let that number settle in your mind for a moment. 4 normally aspirated engines, no turbochargers, no superchargers, producing nearly 3,000 combined horsepower in 1968. The engineering sophistication required to make 4 Camrys work in concert, sharing a common drivetrain, managing heat and vibration and fuel delivery for all 4 engines simultaneously, was extraordinary.
So let's talk about legacy, because the camera's influence didn't end when the last one rolled off Ford's assembly line. In fact, you could argue that the camera's most important contributions happened after it stopped being produced. When Ford developed the 385 series engine family in the late 1960s, which included the 429 and 460 big blocks that would power everything from Mustang Boss 429s to Lincoln Continentals, the engineers incorporated lessons learned directly from the camera development. The port designs were influenced by the smoke flow visualization research done for the camera heads. The combustion chamber shapes reflected insights gained from the camera's hemispherical chamber experiments. The bottom end was beefed up based on stress analysis first performed during camera testing. The Cleveland small block heads, the ones fitted to the legendary 351 Cleveland engine that enthusiasts still worship today, used port designs that were directly descended from camera research. The Cleveland's canted valve arrangement and high-flow ports were essentially a scaled-down, simplified version of what Ford had learned, making the camera breathe. When engine builders today talk about the Cleveland having some of the best flowing heads Ford ever made, they're indirectly praising the camera's engineering DNA. Fast forward even further. When Ford developed the Voodoo engine for the 2016 Shelby GT350, a flat-plane crank 5.2-liter V8 that revved to 8,250 RPM, the engineering team studied camera port designs as part of their research. The Predator engine in the current GT500, a supercharged 5.2-liter making 760 horsepower, uses valve angles that were inspired by the camera's 14-degree valve angle research. Even the Coyote engine, Ford's bread-and-butter modern V8, carries indirect genetic material from the camera through decades of accumulated knowledge about airflow, combustion chamber design, and valve train dynamics. But I want to step back from the technical details for a moment and talk about what the camera ban really meant for American motorsport, because this is where it gets really interesting from a philosophical perspective. The camera ban forced NASCAR to answer a fundamental question about its own identity. What is stock car racing supposed to be? Is it a technology showcase where the most advanced engineering wins? Or is it a competition where driver skill and team strategy matter more than engineering budgets?
Bill France chose the second option. And whether you agree with that choice or not, it had enormous consequences. By banning the camera and establishing the precedent that overhead cam technology was not welcome in NASCAR, France created a philosophical framework that has governed the series for 6 decades. Even today, in 2024, the NASCAR Next Gen car uses pushrod V8 engines based on architecture that would have been familiar to engineers in the 1950s. Every manufacturer that participates in NASCAR, whether it's Ford, Chevrolet, or Toyota, builds their racing engines around pushrod valve trains. Toyota, a company whose entire production lineup uses overhead cam engines, builds a pushrod V8 specifically for NASCAR. That's the camera's shadow, stretching across 60 years of racing. Now, you might be thinking that France was wrong, that he held back progress, that he chose the past over the future, that he denied fans the chance to see the absolute bleeding edge of automotive technology competing on oval tracks. And there's a legitimate argument for that position. But consider the alternative. Look at what happened to open-wheel racing in America. IndyCar allowed overhead cams, turbocharging, and increasingly exotic engine technology. By the 1990s, the costs had spiraled so high that only factory-backed teams could compete. The grid shrank. Independent teams disappeared. The series split into 2 competing sanctioning bodies, nearly destroying American open-wheel racing entirely. The engineering arms race that produced incredible technology also produced a sport that was increasingly inaccessible to anyone without a multi-million-dollar budget. NASCAR, for all its stubbornness about pushrod engines and restrictor plates and rules that seemed designed to prevent anyone from gaining a technological advantage, remained accessible. Independent team owners like Bud Moore and Junior Johnson could compete against factory teams because the technology was constrained. A talented driver in a well-prepared but modestly funded car could beat a factory team on any given Sunday. That competitive balance, which France valued above everything else, was preserved precisely because engines like the Camry were kept out. There's a quote attributed to Bud Moore that puts this in perspective. He reportedly estimated that switching his 2-car team to Camry engines would have cost approximately $100,000 in 1964 dollars. Adjusted for inflation, that's nearly $1 million today.
And that was just the engine cost. The Camry required different transmissions because of its power delivery characteristics. It needed different rear-end gear ratios. The suspension had to be revised to handle the additional power and the different weight distribution created by the aluminum heads and overhead cam hardware. A team that couldn't afford the Camry conversion would simply be unable to compete. The field would shrink to a handful of factory-backed teams, and NASCAR would become exactly what France feared, a rich man's playground. There was also the practical matter of reliability and maintenance. Ford's factory teams had the resources and expertise to maintain Camrys properly. Those long timing chains required adjustment every 500 miles. The valve springs needed replacement every 1,000 miles. The overhead cam bearings needed regular inspection and measurement. A missed maintenance interval didn't just cost performance, it meant catastrophic engine failure. An independent team running a Camry without Ford's engineering support would be playing Russian roulette every race weekend. You could argue that the Camry ban was the most important competitive balance measure in NASCAR history, more impactful than restrictor plates, more significant than the common template, more consequential than the current next-gen spec chassis. Let me take you through one more thread of the story that rarely gets told. When Ford was blocked from NASCAR, they didn't just redirect resources to drag racing and land speed records. They poured money and engineering talent into the GT40 program, the audacious effort to beat Ferrari at the 24 Hours of Le Mans. Many of the same engineers who developed the Camry transitioned directly to the GT40 program. The knowledge they'd gained about airflow, combustion dynamics, valve train design, and engine management directly influenced the development of the GT40's racing engines. First, the 427 FE-based engine, and later the small block 302 that powered the GT40 Mark IV to victory.
Ford won Le Mans 4 consecutive times from 1966 to 1969, one of the most dominant runs in endurance racing history. And while the GT40's engines were pushrod designs, not overhead cam, they benefited enormously from the research and development done during the Camry program. The GT40 victories are often cited as one of the greatest achievements in American motorsport. They wouldn't have happened, at least not in the way they did, without the Camry ban redirecting Ford's engineering resources. This is where it gets really interesting from a historical what-if perspective. There's a parallel universe where NASCAR approved the Camry for competition in 1964. In that universe, Ford dominates the 1964 and 1965 NASCAR seasons so completely that Chrysler follows through on their threat to withdraw. General Motors, unable to develop an overhead cam answer quickly enough, also pulls back from their under-the-table racing support. NASCAR is left with a one-manufacturer series. Attendance plummets. Television contracts dry up. The sport that Bill France built from bootlegger origins into a national phenomenon collapses under the weight of one engine's technological superiority. Or maybe not. Maybe Chrysler develops their own overhead cam Hemi. Maybe GM accelerates the development of what would eventually become overhead cam engines in their production lineup. Maybe the engineering war produces engines making 800 or 1,000 horsepower by 1970, and NASCAR becomes the most technologically advanced racing series in the world. Maybe stock car racing becomes so spectacular that it overtakes Formula One as the global pinnacle of motorsport technology. We'll never know. What we do know is that the Camry forced a choice, and that choice defined American stock car racing for the next 6 decades and counting. Today, original Ford 427 SOHC Camry engines are among the most valuable and sought-after pieces of American racing history. Complete, documented engines regularly sell for between $50,000 and $75,000. Engines with verified racing provenance, particularly those that can be traced to specific drag racing or land speed record campaigns, command even higher prices. Of the approximately 500 production Camrys Ford built, historians estimate that fewer than 100 complete engines survive. Many were destroyed in drag racing accidents. Others were dismantled for parts when replacement components became unavailable. Some simply disappeared into private collections and haven't been seen in decades. Ford kept serial number 1,
the very first production camera engine, and it now sits in the Henry Ford Museum in Dearborn. The polished aluminum heads gleam under the museum lights. The massive timing chain covers hint at the complexity hiding underneath. The placard describes its horsepower, its technical innovations, its racing achievements in drag racing and land speed competition. What the placard doesn't mention, and what makes the camera such a poignant artifact, is that this engine never turned a single competitive lap in the racing series it was designed to dominate. It was built to win at Daytona and Darlington and Charlotte. Instead, it conquered drag strips and salt flats and Vietnamese rivers. That's the camera's strange, brilliant, frustrating legacy. Too advanced for its intended purpose, too good to be allowed to compete, too important to be forgotten. The Ford 427 SOHC Camry remains the greatest what-if in NASCAR history, an engine that changed everything by racing nowhere.